not only for the health of our companies, not only for our professional careers, but also I believe for the earth. That's our only home. And given the climate crisis and energy crisis, I think that as electrical engineers, we have a strong responsibility to help improve the situation. And said that, if we look into electricity, it's everywhere nowadays. As we know, every year we produce almost 30,000 of terawatt hours of electricity. So it's a significant number. We harvest it through renewable sources like solar, wind, hydro, and still through some non-renewable sources as well. And we utilize this in many, many applications for our homes, for lighting, heating, cooling, for charging our devices, for our data centers, for the internet, for the nascent artificial intelligence that's growing really fast nowadays, for our industries, for the motors that goes in pumps, in turbines, in robots, and of course for our vehicles that are getting electrified more and more. And as we know, we have to always transform and convert the shape of electricity from AC to DC and vice versa, from low voltage to high voltage and vice versa. And in each of these steps that you can see here, the efficiency for conversion today is between 85 and 97%. So this seems a large number, but actually it's not enough. We can do much better than this, because even 1% of a big number can make a huge impact on climate. And so today, what we're going to see is how we can improve the situation. And so very briefly, we're going to go through what are the losses that we incur in transistors, how GaN can improve the situation thanks to its properties. And then we're going to go through the current range of today current GaN devices. And for the future, I'm going to talk about a high voltage GaN with 1200 volt devices, and a very exciting bidirectional GaN, which is a very unique device that only GaN can do. And then I want to leave ample time for a Q&A at the end to hear from you. So if we dive into a power converter, today this is an example of electric vehicle. So we have the wall plug, we have an onboard charger. The first stage has an EMI filter and a power factor correction, which is an AC to DC stage. Then we have a DC link capacitor to stabilize the voltage right here. And then at the second stage of our charger, we have a DC to DC topology, which is isolated with a transformer for galvanic isolation between the input and the output. And this is to give basically the right voltage to the battery. Then, of course, you have the battery, and if you have a motor, you have an inverter to convert DC voltage again into AC to spin the wheels. As you can see here, we have one section of the charger which is in hard switching, which is kind of the worst case, and I'm going to show you later. And then we have the DC to DC is in a resonant converter, so it's a little better, it has a little lower losses, but still we can improve it with GaN. And as you can see here, we have inductors, you have capacitors, transformers, and what you can see is a lot of transistors. So really optimizing the transistor is key to improve the efficiency of conversion. And so if you look at a transistor, in its ideal case, it behaves as a switch. So it's off and on, and there's no power dissipation, no power losses in the off state, not in the on state. It switches instantaneously. And so we never go into this area of high power dissipation you can see here with these contour lines. But as you know, in reality, a switch has losses. In the off state, eventually begins to break down and it goes into this high power dissipation. In the on state, there's an internal resistor that dissipates energy, and most importantly, the switching between on and off is not instantaneous, but takes some time. And so you're spending some time in this high power region right here in these red power lines here. And the reason why That happens, as you may know, is because the transistor has internal parasitics, capacitances between the terminals and the inductances. And so that slows down the transition in current and in voltage, because every time we switch, we need to charge and discharge these capacitors and inductors, and that makes the transition not instantaneous. And so in the hard switching case, which is the worst case shown here, you have a situation where you're switching where you have both high current and high voltage, and that gives rise to a spike in power that you can see here. These are the so-called switching losses that we need to minimize. And when the transistor is fully on, then you have power dissipation on the internal resistances, and these are the so-called conduction losses that are a function of the internal RDS on. Of course, as engineers, the key trade-off here, there's always a trade-off between the conduction losses and the switching losses. In fact, if you take a conventional transistor, like here we have a vertical silicon device, and if we try to reduce the resistance, we need to make the active area bigger. So by making the active area bigger, we can reduce the resistance. But as the area increases, the capacitance increases too. And so the switching losses now are going to increase. And so you can see that there's a minimum, an optimum minimum, below which we cannot go. So you can see that a certain active area will just give us the minimum of conduction and switching losses for silicon. Now, what GaN allows us to do is to alleviate this trade-off. And for the same active area, we see that we have much less resistance. So GaN for the same area gives you much less resistance. And that means that now the minimum of the power losses is at a much lower position. So we see we have a lower resistance, lower capacitance, a smaller active area, and a smaller total power losses. And if you want to go and see in on the data sheets on the web, you can compare silicon devices like here with this super junction with GaN, and you can see that for the same voltage rating or even more voltage rating for GaN, GaN has lower resistance and lower capacitances and lower charge. So that makes GaN ideal for both lower conduction losses and switching losses at the same time. So I invite you to go on the web and compare different data sheets to have that understanding for yourself. It's really eye-opening. Now, how can we do this improvement with GaN? Now I can try to go to the next slide. And so this is the GaN device architecture. I'm sure most of you are already aware of it. It's a lateral transistor, so we have source, gate, and drain at the top. And the transistor is grown on a foreign substrate, which can be silicon or sapphire. Silicon for a 6-inch wafer, very high diameter wafer, low cost, very high manufacturing capabilities. Of course, there's a buffer layer to isolate the active area from the silicon. Sorry, slightly there's some background noise.
Yeah, someone needs to mute. I think there's okay. Let me try to see this.
Excellent, excellent. That's where some
Yeah.
dinner time at home.
Yeah. Yeah, you can continue. Yeah.
Excellent. So, and if you look at the active region, of course, we are all aware of it. We have an AlGaN layer on top of GaN, very thin layer of AlGaN. And you can see here the interface done on a TEM imaging, the very sharp interface, very pristine, high quality atomic layer precision. And so this quality of interface with the fact that both AlGaN and GaN are undoped, so there is no impurity doping, but the doping comes from polarization. As you know, we have very good quality channel of electrons at this interface. As you know, it's the two-dimensional electron gas with a very high density, one E13 charge, and with an extraordinary mobility, which is 2000 centimeters square volt per second. And the mobility is very high because it's a very high quality interface with no doping and no scattering. For comparison, silicon mobility is around 500 to 1000, and silicon carbide is between 50 to 800. So having a high mobility channel is the first reason why GaN have a lower resistance for the same chip area. So that's number one very important fact. Mobility is really a God-given parameter to GaN. And the second reason is, of course, the breakdown field. Being a wide bandgap semiconductor, we have a very high breakdown field of 3.3 megavolt per centimeter, which is 10 times more than silicon. So which means that we can pack the same voltage in a much smaller area, therefore again minimizing the resistance of that device. And so you can see here, in this instance, the gate is isolated with the dielectric, and also you can see the feed plate structure, which is used to basically spread the electric field across the gate to drain distance. And so we can get a better engineering, a better spreading of the field through the device without any peaks that could damage the device prematurely. So this is a very well-known technology. And now, so again, this transistor looks like a great transistor, but everything in nature comes with trade-offs. And the trade-off of this transistor is that it's a normally on device, which means that the channel is spontaneously present. And if you want to pinch off the channel, we need to apply a negative gate bias to turn off the device. But as we know, this is not ideal in power electronics for safety reasons. For safety reasons, we need to have a normally off device, a device that is off at 0 volt, and we turn it on with a positive gate bias. And so that's where the industry went for the last 2 decades and did a lot of R&D, explore many different architectures. And at the end, after almost 20 years of investigation, it boils down to two main device architectures. There's the so-called D mode, which is a two-chip normally off device. So we take the same device I showed you before, which is a normally on HAMD with the electric, and we put it into a cascode configuration with a low voltage, normally off silicon FET. So we are driving the silicon FET, which can have a very high threshold, up to 4 volts, very robust and reliable thanks to the quality of the silicon gate. And the high voltage section is done in GaN. So we have the performance of GaN with the robustness and threshold voltage of silicon FET. A few things to say: the channel resistance can be as lower than 350 ohms per square, so we can really optimize the channel resistance because it's not connected to threshold. So threshold and resistance are separate, so we can tune them separately, which is a very good feature of the cascode architecture. And as we know, a very robust gate, so it's off with 0 volt, we turn it on at 8 volts, and then there's plenty of headroom up to 20 volts for robustness and reliability. The other architecture that's been successful in the industry, you can see on the left, is the so-called E-mode device, which is a single chip, normally off. And to do that, the first thing is engineers have to reduce the charge density in the channel, so resistance actually goes up. So the resistance of an E-mode chip can be 500 ohms per square or more, and that's because there's a trade-off between threshold and resistance. If the charge is too high, the threshold will become negative. And then, of course, they have to have a p-type GaN under the gate to deplete charge under the gate and have a normally off device. So threshold voltage is 1.7 volts, which is barely enough to keep it off, which is enough to be successful in the market. The key thing here is that now the gate is not isolated. You see there's no dielectric between the gate and the semiconductor. So that means that now we have a reduced gate margin. So because the threshold is low, we need a negative gate drive to turn it fully off and for switching during applications. We turn it on at 6 volts, but we see that at 7, it's already the maximum. So that's posing some limitations on how we drive it and how careful we have to be with this device. Said that, this is a great technology. The E-mode is a great technology for low voltage applications, 100 volt, 200 volts. This E-mode dominates. For higher voltages in the 650 volt range, we see both. And as Renesas, we have the cascode technology. We have good elements to believe that the cascode is superior. And I'm going to describe it to you in the next slide. So let's go under the hood of the D mode to chip normally off solution. I want to show you how the transform engineers and now Renesas made this solution successful. And so you can see here, this is the assembly, and you can see that we have the GaN chip that's at the bottom with the drain terminals. And the silicon chip, actually, it is assembled on top of GaN. So it's a stacked die architecture. Silicon is a vertical trench MOSFET, and so the drain of the silicon is underneath this silicon chip. And so this connection is realized without any wire bonds. So it is a stacked die solution. And when you put it into a package, you can see it's a very elegant architecture, and we have the wire bonds for the gate, for the source, and for the drain. And if you look at it from here, it basically looks like a single chip solution. It has no extra wire bonds for the cascode. It has only wire for the gate, for the source, and for the drain. It's a very elegant solution that gives us fast switching, low ringing, with the reliability of the silicon FET. And just for those of you who wonders, the contribution of the silicon FET on the total resistance and capacitance is less than 10%. The silicon FET is less than 30 volt, so it's a very, very optimized for resistance and capacitance. And the high voltage is all taken by GaN, which is optimized for fast switching with a high mobility channel. Now, to give you an idea of a product portfolio of what can be done with the cascode technology, here you can see the product portfolio with the rated current and the rated on-state resistance. And you can see that the smallest chips, they have a resistance of almost 500 milliohm, and they can carry 3 or 4 amps of current. And these are sufficient for the low power applications like cell phone chargers, for example. So this is the low power cell phone charger, laptop charger devices. Then we have a medium power between 25 amps and 46 amps here, which are used in power supplies for data centers. And our biggest chips for high power are a 15 million product, and we have a 10 million prototype today. 10 million prototype can carry as high as 170 amps of current. So you can see that it's getting significant. It's getting very seriously high, and to the point that it could compete against silicon carbide as well. And of course, if you need even more current, you can always parallel chips, and we have demonstrated, we're going to publish data on paralleling cascode chips to achieve 350 amps or 700 amps of current. You can see here a module integration by Kyocera. This is a 500 amp GaN module, and it's claimed to have cascode inside. And thanks to our sources, we think that there's transform GaN in this package. So very elegant automotive package with GaN cascode in it. I just want to give you now some data on our latest prototype of the 10 million. So we took our 10 million, which is a 650 volt rated. It's packaged in a very simple TO2473 lead, just as a test vehicle for switching. And we put into a boost converter. So we stressed it in the hard switching, which is the most stressful condition. And you can see here the waveforms and the efficiency curve. And we got 99.3% peak efficiency, which is significant. And we were able to sweep all the way to 14 kilowatts of power. And the junction temperature was only 120 Celsius. So there was still margin for further increase in power. So to me, this one is a great result. Just with one transistor, we can have great efficiency up to a very high power density. Of course, this is 50 kilohertz. We have data also to higher frequencies, and that is behaving well too. So this is a very promising result. I just wanted to showcase it with you today. This one is in, as we said, in a TO package, which is a great package for thermal, very high thermal dissipation. It's a classic package that goes into all the standard traditional designs for boards. And for the future, what we see from customers is an increasing interest in surface mount packages. And so you can see here the portfolio of Cascode in surface mount, which is like PQFN or the TOL or the TOL-T. And the surface mount packages have two advantages. One is less inductance of the leads. So less inductance means even faster and more efficient switching. And also we have a Kelvin source on the package. So the Kelvin source helps by minimizing the gate loop inductance. As you can see here, we offer them both in a bottom side cooling, where the heat sink is at the bottom of the package. So you can see here the cross section with the silicon fat, the GaN HAMT, the lead frame of the package, and then the circuit engineer has to make thermal vias through the PCB to extract heat through the board, and you can see the heat sink on the other side of the PCB. This one, of course, is a trade-off because thermal vias are more expensive and they take space that we cannot use for electrical routing. And so a very popular demand that's coming is the top-side cooling, where now you can see the chip is basically the package is flipped upside down. So now the silicon fat, the HAMT, the lead frame is facing up, and now we can put the heatsink on top of the package and leave the PCB free to be used for electrical routing. So this is decoupling the electrical from the thermal management, and it's a very elegant solution, and we see a lot of interest from this technology. Today we have the TOL-T, which is a package that can host 70 million down to 35 million. And for the future, just as a preview, there's consideration of the QD pack, which is a bigger version of the TOL-T. And so with a bigger version of this package, we can accommodate bigger chips like a 15 million or a 10 million or other chips that I'm going to show you in the next slides. Of course, if you want to go into applications, reliability is key. And so we have made extensive qualifications and reliability campaigns. So our products are JERE qualified and automotive qualified. And key results here, you can see the high temperature reverse bias, 1,000 hours, 650 volt to 175 C. We need to do 3 lots, 77 parts each, and have no failures to pass. And so you can see here we had no fuse failures, and you can see the dynamic around shifts is really small after the stress, so really strong and robust technology. I want to focus your attention on the high temperature gate bias. So these are 1,000 hours, 20 volts on the gate at 175 C. And again, we had no fuse failures and no shift in the parameters, so no gate leakage increase and no shift in threshold, which is very stable at 4 volts. And of course, we have the high temperature operating lifetime, where we do reliability in switching conditions. Here, you can see 100 kilohertz in the boost converter. And again, no fuse failures, no parametric failures. And I want to show you the threshold right here. Basically, it's very pinned, very stable with less than 1% shift. So spectacularly stable for this device, thanks to the silicon MOSFET and its technology. So thanks to the reliability and the quality of these devices, we witnessed market adoption. So you can see here across the years, we see how GaN, our transform GaN is penetrating the market. So with significant field hours, 21 million parts already in the market in applications that go from 45 watts to 7.5 kilowatts. With exceptional performance and a failure rate which is as good as silicon. So this is a great start, but as we know, this is only the beginning. Power electronics is booming, and GaN can really play a role in many more applications than today. And thanks to this, as you know, in June 2024, Transform became Renesas. And we believe that from a small business, now we have a big company that can support us penetrating the market even further. So this is a great news for GaN in general. So this is a snapshot for the present. And now I want to give you a peek. I want to give you some outlook on the future of the technology. And so the first thing I want to talk about is the voltage rating. And today, as we said, we have 650 volt GaN on silicon technology. And you can see here on off state curve of the device, and you can see that the leakage begins to increase at around 900, 1000 volt. And the reason why there's leakage beyond 900 volt is not because of avalanche, because we don't have any PGAN, there's no avalanche in lateral GaN, but because of the leakage between the drain and the substrate, which is connected to the source. So beyond 900 volt, we have leakage between drain and substrate. And so that's why we are rating the device very safely. So the DC rating is 650 volt, and then we have a transient rating at 800 volts that is there to allow any spikes or any overshoots to make any over voltage to make the device reliable and robust to these events. But of course, the industry is requiring not only 650 volt devices, but also 1200 volt devices. And that's where Transform had the insight. This was a few years ago, to design a 1200 volt lateral GaN HEMT. And to do that, the idea was to replace the conductive substrate, like silicon, with an insulating substrate, like sapphire. So with sapphire, which is insulating, we are basically eliminating the leakage path between the drain and the substrate, therefore further increasing the voltage rating of the device. And a few things here. The sapphire, as it's really known to have a higher thermal resistivity. So to have the same thermal performance of silicon, sapphire needs to be thinned, but that is okay because sapphire is a very stiff, a very hard material, so we can thin it without breaking the wafer. So that's been demonstrated. The second thing is that now the buffer, because there's no leakage between drain and substrate, can be much thinner. So if this one is a few microns, on sapphire, it can be less than half of that. So again, we can save on epi time. The emissivity growth can be significantly shorter on sapphire because we don't need a thick buffer. Cost is very competitive. Sapphire cost is now very low because sapphire is used for LEDs. So the whole infrastructure, the whole manufacturing is existing for LEDs, and we're just riding that infrastructure with a low cost. And of course, for 1200 volt, the only thing you need to do is to increase the feed plate to drain spacing to have the right lateral breakdown here. So very promising technology. Demonstrated here thanks to ARPA funds. You can see here a 6-inch wafer, again on sapphire. You can see now the leakage curve has the knee voltage is at 1400 volts. So you can see that at 1200 volts, we're still in the flat regions, very promising. And from the very first data points is already competitive with silicon carbide. So this is just the first iteration. Now we're going through the next iteration to improve performance even more. And if you're worried about the wafer diameter, be aware that there's already a report in the literature about GaN amps on 8-inch sapphire. So sapphire is future-proof, so it can be scaled from 6 to 8-inch to further reduce the cost of manufacturing. So very exciting technology. The next technology for the future is the bidirectional GaN switch, which is monolithic integration. And so thanks to the lateral architecture of GaN, what we can do is that we can integrate in the same chip, we can integrate two switches back to back. So you can see here, there are two sources, there are two feed plates with a common drain, and you can see that the drift region between these two switches now is shared. And so that means that we can have much less resistance than having two separate chips connected back to back. And so, of course, this one is in a cascade architecture. So you see the monolithic GaN integration with the two silicon FETs on each side. And again, we demonstrated it thanks to government funds. You can see here a prototype of a 17 milliohm 650 volt bidirectional switch with two sources and two gates. And the way it's assembled is as before. We have the GaN chip with the two silicon FETs on top of it. So we don't have any additional area or additional wire bonds for the cascade configuration. And so you can see here data, we have bidirectional current flow, so we can flow current in both directions. And most importantly, we have bidirectional voltage blocking capability. So we can block voltage both in the positive voltage and the negative voltage. So this is a very important feature. And the reason is coming in the next slide. So why these devices are important. So let's go back to the topology. So at the beginning, I showed you a converted topology, which is an AC to DC. And today, as we said, it happens in two stages. We have a first AC to DC stage. We have a DC link capacitor, and then we have a isolated DC to DC stage. And so it has a certain number of transistors, and it has a big DC link capacitor in the middle. But there are topologies in the literature that actually can do the same thing with a single stage. And so you can see here, it is a rearranging of the architecture. And now you can see that at the primary side, the one facing the AC, we don't have the DC link anymore. But now we have transistors connected back to back because they're back to back because now we need to block the AC voltage both in the positive lobe and the negative lobe. So this is a topology that allows to remove the DC link capacitor. However, you can see that if you do it with discrete devices, now you have more transistors. So here there's more transistor count, and so it becomes a little bit cumbersome. But with GaN, the beauty of GaN is now that we can take those back-to-back transistors and integrate them in one single package, in one single chip. And so that's how GaN bidirectional makes this topology very attractive, because now you don't have the DC link capacitor, and actually you have less transistor count. You go from 10 transistor on this topology to 6 transistors on this topology. So very attractive solution for the future. And just to make you appreciate what's the impact of the monolithic integration. So let's take here a single device, let's call it a 70 million unidirectional device, and it has 1 times the specific Aron. So it has a certain chip size. This is Gen 4, the transform Gen 4. If you want now to make a back-to-back connection using bidirectional devices and still keep a total resistance of 70 million, you see that now you need 4 times the area, because now you have 70 back-to-back, that becomes 140, and then you need to have 2 more in parallel to go back to 70. So you see that back-to-back connection gives you a 4 times increase in chip area if you do it with discrete devices. If you do it with the monolithic integration, you can see actually that we can do a 70 million bidirectional GaN with only a 1.8x increase in specific Aron. So it is a significant improvement from discrete to a monolithic integration. So you can see here the symbol of the monolithic GaN bidirectional switch with the 2 sources, the 2 gates, and here you can also see the 2 Kelvin sources that will come in the next generation of products. So very exciting technology, stay tuned, because this is what I believe differentiates GaN from everything else. Silicon cannot do monolithic bidirectional integration, and silicon carbide also cannot do this device. This device is only be possible with GaN. So very exciting for me as a technology. And just to give you an idea of how it works in applications, we provided the bidirectional GaN switches to the University of Padova back in Europe, and they demonstrated this single stage AC to DC converter with the bidirectional GaN on the AC side. And you can see here 50 kilohertz switching with clean switching waveforms, and you can see here the AC input, which is 3-phase, and a very clean DC output. This was a 96.1 efficiency at 1.6 kilowatt, and there is margin for improvement in efficiency. As you can see at the secondary, they're still having a diode bridge that was just for test purposes. So you can see that the diodes contribute to a significant portion of the losses. In the next generation, they're going to replace the diodes with an active bridge and removing the diode losses. So very promising demonstration, and so stay tuned because more will come. These samples are available, so if you're interested, we can discuss shipment of the samples. Applications of these topology are many. So we see a lot of interest from energy harvesting, like solar panels and solar inverters. They would strongly benefit from GaN bidirectional and these topologies, but also battery systems to charge your vehicles, or to charge any other batteries in your home with the bidirectional functionality. So you can do grid to the battery or vice versa. So very big market in battery systems. And of course, the other one huge is the data centers, not only for the internet, but also for artificial intelligence. So many opportunities, and I'm sure that in the near future you see GaN unidirectional and bidirectional penetrating these markets. And with this, I'd like to conclude to leave ample time for questions. And just want to give a few numbers. If we replace all the power converters using wide bandgap semiconductors like GaN and silicon carbide, the efficiency can go from 85 to 97% to 95, 99%. So it can be a significant improvement in efficiency. And that means that each year we can actually save, according to the predictions, 630 terawatt hours of electricity. And just to give you a reference, this number is similar to the savings that LEDs brought to lighting. So when the world replaced bulb lighting with LEDs, they got a similar savings in energy. It was about 500 or 600 terawatt hours a year. So the same story can happen for power electronics. By replacing silicon with GaN and silicon carbide, we can get the same impact that got LEDs in the lighting. So very exciting for us. And as I always like to say, this is not only for us, for the people, because it can give us smaller converters, more efficient converters for our cars and our cell phones. But again, very importantly for the planet, which needs all our help today. So with this, I'd like to conclude the talk, and I'm here to have a discussion with you on a Q&A. Thank you everybody for listening.
Thank you so much, Davide. It's very very nice talk. Covered the fundamentals so well and went into some of this
Thank you.
more advanced topics. So I'll now request the audience, if they have any questions, to either type it in the chat box or raise their hands, and we can go one by one. Yeah. So Shant Mittal, you can unmute yourself and go ahead.
Yeah, hi. That was a very nice talk, David. I have a question. You didn't touch much on the E-gate GaN hemp based on the P-GaN. So, so I would like to know what is the status of particular device and in industry, and where does it stand? And and do we have some products based on it already? And like there are some issues about magnesium doping and I think getting it ionized and controlling it properly. So like
Mhm.
what are the challenges there, and lateral avalanche breakdown, not just vertical. So maybe you can just shed some light on that.
Yeah, sure. I think that's great. We can talk about that. I would say I think I have a slide. Let me just see here. So there are two things about the E mode. So nowadays, the E mode is well used in the low voltage applications. So let me go back to the cross section right here. So in the low voltage domain, so 100 to 200 volts, this is the technology as of today. It's a very well calibrated technology, so magnesium doping is not an issue. They found out the right processing sequences to activate the magnesium to get the right threshold. And so on the fabrication side, I think everything is under control. I would say if I would have to point out a few challenges that are not a big issue for low voltage, but can be a problem for high voltage, is that so the gate is not isolated. And so at the beginning, so there was a technology, it was called GIT, and there was an ohmic connection between the gate and the PGAN. But that connection was very leaky. So when you turn on the device, there was significant gate current. And so that is very delicate, not maybe suitable for high voltages. And so the next generation of EMO devices, they put a Schottky contact between the gate and the PGAN to minimize the gate leakage. But now, if you put a Schottky contact between the gate and the PGAN, you see that you start having a back-to-back junction. So you have a junction between the PGAN and the 2DAG, and a junction between the PGAN and the gate. Now, if I go back to this slide here, if you have a back-to-back junction on the gate, you see that when it's time to charge and discharge the CGD, current now has to flow through a back-to-back junction. And so that's not easy. Current here is blocked in both ways. And so what that means is that when you're switching the device from off to on, there is residual charge that's been trapped in between these two junctions. and the residual charge is like negatively ionized, and so that is debiasing the channel. And so what gives you is actually dynamic around. So the device does not turn on fully because you have trapped charge in between these two junctions. And so if you look at the data, if you do dynamic around of a Schottky E mode, you see that that's like almost 30% of the static. Whereas if you do the same measurement on a cascode or even an E mode with an ohmic contact, the resistance is much better. So this one is a challenge. I know that they are making progress on this, but this has been one of the key challenges for E mode.
Okay, Mriganko, if you're not
Yeah,
there, maybe. Yeah,
it
okay,
was
go
pleasure
ahead.
listening to your talk. Well, yes, my question is, if I have to use for a low voltage in radiation environment, so GaN will perform better or silicon will perform better, say around 10 to 15 voltage of power supply. And the second question is, do we have PDK available for GaN, which universities can use for designing of?
Okay. So yeah, thank you so much for the question. So the first question is about the low voltage, and so you're saying 10, 15 volts of device rating. Is that you're asking whether
I think
GaN?
the question was something on the radiation hardened performance comparison.
Oh,
Yeah.
okay, excellent. Yeah, so GaN is being a wide bandgap material is of course more radiation tolerant than the silicon devices. For low voltage, I would say yes. And if you need low voltage applications, again, the E mode is the preferred way to go. You don't need a cascode if you just need 10, 15 volts of total voltage with a single chip E mode that can do it nicely. And I can say that yes, it's radiation tolerant, and there are of course continuous improvement, and but it's already very well positioned. And for the PDK, I would say that there are foundries that yes, they have PDKs. So Renesas, the business model of Renesas is that today we don't have a PDK, so we don't open the process to customers. We sell the final solution, so you can ask us to design a product for you if you have a sufficient market. Or but if you want to design your own GaN, there are already GaN foundries in the world that can help you with that, especially low voltage. There's many foundries that can help you with that. But if you want the solution, Renesas can offer it. So if you have business ideas or market cases, you can email me, and I'll be happy to take it from there.
Right. Thank you. The next question is one in the chat box, and I think that's something you might have heard many times before. Can you compare GaN and silicon carbide in terms of cost efficiency?
Yeah,
And also compare, and a related question from another person is compare GaN and silicon carbide performance at peak temperature.
yeah, perfect. Yeah, I have both those answers. So let's start from the comparison of GaN and silicon carbide. So you can see here, this is a vertical silicon carbide device compared to the GaN lateral device. And the key difference, there are two differences, of course. The silicon carbide is a vertical device, so it's blocking voltage vertically. The GaN is lateral device, so it's blocking voltage laterally. The second difference is the mobility. So if you look at the mobility of the silicon carbide device in the channel, where you have basically electrons flowing at a p-GaN oxide interface. Mobility can be as low as 50 centimeters square per second. And just to give you an idea, so this is a TM cross section of a silicon dioxide silicon carbide interface. You can see it's pretty, there's some bumps, and that's what makes mobility low in this channel, because electrons have to go through these bumps. Whereas on GaN, a very pristine interface, so electrons can zip at very high mobility through that interface. And so because of the higher mobility, and so the gate is 50 for silicon carbide and 800 for the drift region. In GaN, we have 2000 for the drift region. And even if you have a cascode configuration, the silicon FET, the mobility is 500. So it's already 10 times higher than silicon carbide. So because of this, you know that the conductivity is a product of charge density times mobility. So you can understand that if mobility is low, charge density has to be high. But if charge density is high, it means that capacitance is high. And so if you compare silicon carbide and GaN, especially in the QG, because the gate is really where silicon carbide has mobility needs improvement. You see the gate for the same voltage rating and the same Ron, GaN has a significantly smaller gate charge because it has a higher mobility in the gate. So that's the difference number one. Regarding the cost, so silicon carbide is a more expensive substrate than silicon and sapphire. So the cost, silicon carbide is a little higher, but again, that depends on the manufacturing and the infrastructure and the industry. So it really depends on your supply chain. But from a physical point of view, from pure physics, if you optimize both materials to the extreme, GaN on silicon or GaN on sapphire physically should be less expensive than silicon carbide because it takes less energy to make it. It boils down to how much energy you need to put into the manufacturing to get this. So ultimately, GaN could be cheaper than silicon carbide, but of course, we need to let time make its course, and the future will tell. So I don't want to be too much unbalanced, especially as of right now with Renesas. We have both silicon carbide and GaN, so I should not make too strong of a opinion. And of course, application-wise, certain applications may be better served with silicon carbide, like very high current applications, like the traction inverter. Low frequency could be silicon carbide, whereas high frequency applications where you need all the help from mobility could be served by GaN. So that's how silicon carbide and GaN could split the market, like low frequency, very high power, and high frequency, medium power. Regarding the thermal, your question about the thermal, I had a slide on it. And this one is the temperature coefficient for resistance. And so you can see how the resistance increases as a function of temperature. And you can see, so GaN, for some reason, which is not clear to me yet, but you can see that from 25 Celsius to 150 Celsius, the resistance goes up 2.6 times. With cascode, we see the resistance goes up 1.7, 1.8 times. And you can see that now cascode is same as the trench silicon carbide. Silicon carbide, you can see planar has the smallest coefficient. And the reason why planar has the smallest coefficient is not because it's good at high temperature. It's because it's bad at room temperature. So the mobility is so low that it has a limited impact on temperature. Trench silicon carbide, they're improving the mobility. So definitely they're making progress on the mobility of the channel. And now you see that the temperature coefficient becomes more like a normal power device. So cascode is 1.7, trench silicon carbide is 1.7. If you look at silicon CoolMOS, again, it's like about 2. So this is eventually could be the zone where all the semiconductors will align.
Right. Thank you, Davide. The next question is on the monolithic bidirectional device we talked about. So the question is from Pooja Sharma, and she asks that, can you please comment on why silicon carbide or silicon is not suitable for this kind of monolithic bidirectional devices? Is it only because the devices are vertical, or is there any other reason?
Exactly. Yes, and thank you for the question. And that's exactly the reason. So if you see here a vertical device, and if you want to do a bidirectional device, current has to go all the way down to the drain, and then it has to go all the way up on the other side. There's no shortcut. If you make the drift region thinner, your voltage blocking is going to decrease. So with a vertical device, it's going to be a 2x increase in resistance. Whereas with a lateral device, you can, as we saw here, you can merge them together, and the drift region is now shared. So when this device is blocking, the drift region is going to expand this way. And when this device is blocking, it's going to expand this way. So the answer is exactly as you said. So the reason why it's difficult with silicon carbide is because it's a vertical device. With a lateral device, you can do that integration.
Yeah, and there's another related question on this topic, which I think you mentioned about it. Is that, are the devices normally on? If so, how can they be converted to normally off? I think you mentioned that you use a cascode, right?
Yeah, that's correct. So in this case, you can see that the monolithic integration happens in the GaN chip. And because it's normally on, then you need 2 silicon FETs to make them normally off. Now, the thing is that the silicon FET is low voltage, so it does not have, as we said, resistance or charge. Most of the resistance and the charge comes from GaN. So the integration of GaN is actually the key. Once you can monolithically integrate a high voltage section, you've done 90% of the job. The low voltage silicon MOSFET, that is, as we said, it's just 10% of the total resistance and capacitance.
Right. Thank you. So next question is on the circuit side. What are the gate drive? It's a question from Mr. Ganesh. What are the gate drive challenges for E mode and D mode devices? Can you compare the advantages and disadvantages?
Yes, totally. So for gate drivers, if you go back to here, so starting from the D mode, because you have a silicon MOSFET on the gate, basically we can interface using conventional gate drivers because you're driving a silicon MOSFET, so the gate driver does not need any change. So we can have the usual 0 volt turn off. It can turn on at 8 or 12 volts. You can use the usual UVLO. You have the voltage rating of 20 volts. So on the cascode, you can use existing gate drivers. And of course, the gate charge will be much smaller because now the silicon FET that you are looking into is a low voltage FET. So you can use smaller gate drivers. If you are using like 4 amps to drive a silicon superjunction with a cascode GaN. This one is low voltage, so the gate charge is small, so you may need just 1 amp of current. So you can use existing gate drivers, but use less current because of the cascode. For E mode, as we said, you need negative gate drive. It turns on at 6 and the rating is 7, so you need special gate drivers for E mode that are designed specifically for GaN. And of course, they are becoming available, so that's not going to be a problem, especially for low voltage. That's not going to be a problem. Just that, yeah, you need to be aware of the limitations of the voltage rating. And of course, the other very important thing is the gate loop. So you cannot have any inductance on the gate path. If you have any inductance, any stray inductance with E-mode, you're going to have ringing, and you see that the margin is very tight. So if you have ringing and oscillations that always go beyond 7 volts, eventually you run into issues. So the design has to be very well optimized for low inductance. So pay a lot of attention on that. With Cascode, that's you have more margin. There's more tolerance on the driving scheme. And the last thing is on the package. Again, the package for E mode has to be again optimized for inductance. So you have all these die level packages with very small inductance, whereas with Cascode you can do both. You can do conventional packages for traditional applications, or you can put them in surface mount packages. So this gives you more margin. E-mode has to be very well optimized.
Right. Right. I see a raised hand by one audience member, Sunil, Mr. Sunil Krishna. Uh, can you please unmute yourself and ask your question?
Hi, David. Thanks for this information. Actually, I just want to have one basic question. The GaN we are prepared for low voltages and the SiC for high voltage. Is the main reason for the non-isolated gate or the as for SiC is a for the vertical device? These are the main reasons or some other reasons?
So for the E mode, yes. So the main reason is the non-isolated gate. So that's why it's ideal for low voltage. For high voltage, you can use either silicon carbide or cascode GaN. So you can see for high voltage like 650 or 1200 volt, you can use either silicon carbide or cascode GaN because they have an insulated gate, so they give you more robustness for high voltage.
Because I think some brands come with 900-volt GaN devices in market.
That's
So,
correct.
yeah. So that are based on these cascoding.
I'm sorry, I couldn't understand. 900 volt
Those,
devices?
yeah, those devices are based on for GaN, cascoding GaN.
Correct. Correct. Yeah, 900 volt device is a cascode GaN. Yes.
Okay. Okay, thanks. Thanks for this. Thanks, sir. Thank you.
Yeah, I think we have just one final question in the chat box. It says that in back-to-back connected switches requires an extra communication circuit. I think he means commutation circuit. Maybe is this provision there in the GaN switch you've mentioned? I think the commutation. I think the question refers to the fact that this four-quadrant switches, the commutation from the from one switch to the other is a little bit tricky.
Yes.
So is that sort of embedded within your, is the other doing something in the package? I guess not, right?
Yeah. So yes, thank you for the question. Really, really good question. And of course, you have two gates. So you need two gate drivers, one gate driver for the low side of the switch and one gate driver for the high side of the switch. So yes, on the gate driver, you need more of them. So that's why also, QG is important. And for the commutation scheme, yes, I can say that if this one is a very simple commutation scheme, when you do the monolithic GaN, you need more intelligence on the commutation because now you have two gates and you need to make sure that you turn them on and off with the right sequence. So there is more intelligence that goes into it, more engineering, which I find actually very interesting, defining all those sequences. And so to me, that's an opportunity for engineers to develop these commutation schemes for the bidirectional devices. Very, very exciting thing. And I can say that the industry is already there. So you already have commercial customers that are getting familiar with switching to gates. So it needs attention, but it's not a showstopper. It can be done.
Right, thank you. So we will probably take a couple of final, no, two more questions, final questions, because we have gone over the time. So I see a raised hand from Dr. Sukhendu. So Dr. Sukhendu, go ahead.
Thank you, Professor. Thank you, Davide, for your wonderful presentation. If the bidirectionality is not a concern, can you comment on other topologies like vertical GaN and what is its future as a technology trend?
Mm-hmm. Yes, definitely. I had so for vertical GaN, I had a slide, but unfortunately not here. So vertical GaN, now imagine then this one becomes a vertical GaN device. Instead of silicon carbide, we make it in GaN. Now, I want to point your attention to one thing. There's something that's missing in a vertical GaN device. And what is missing in a vertical GaN device is the high electron mobility. So with a vertical GaN, mobility goes down to earth. So in vertical GaN, mobility will be again 50, 100 in the gate and 800 in the drift region. In a vertical GaN, you don't have the advantage of high mobility in the channel. However, said that, with the vertical GaN, you're holding voltage vertically. So that allows you to scale voltage to very high levels, and even silicon carbide. So what vertical devices can do that it's a little more difficult with lateral is to go to very high voltages. So 1200 volt is doable with GaN, but if you think about 5 kilovolt or 10 kilovolt, at that point, vertical may be needed. Lateral could still be doable, so that's the R&D efforts possibly that will come in the future. But vertical for very ultra high voltages could be preferred. The last thing for vertical GaN is the substrate. GaN substrates are still expensive, so I see that as a challenge. There was a big interest 5 to 10 years ago on vertical GaN, but nowadays that interest, at least in the US, it's fading away. I remember 10 years ago I was at UCSB and everybody was doing vertical GaN. Everybody. There were many millions of dollars from the government to develop vertical GaN. Today, if you look at universities doing vertical GaN, there's still somebody doing it, but not as many as in the past. So again, future will tell which technology will win for which application. But these are my points. Look at mobility, look at substrate cost, and as an advantage, look at the voltage blocking in a vertical device.
Thank
Right.
you. Thank you so much.
Thank you, David. I sort of had a small follow-up to that question. Is like you have this medium voltage like grid connected applications, right, where people
Mhm,
are now using 1.7 kV and 3 kV.
mhm,
Silicon carbide is also commercially available now.
mhm.
So is there a sort of a near-time roadmap for lateral GaN in let's say to coming up with the next 1.7 kV GaN
Mhm.
device for grid connected applications?
Yeah, actually, that is a great question. I would say as of today, the roadmap is at 1200. So right now, first we need to make the 1200 volts successful. Once 1200 volt is has succeeded, we can start thinking about 1.7 and higher. It becomes a market and an application space. So as you said, it's going to be great application, so it's a different ecosystem. So time will tell. Today we are at 1200 volt node. The future will tell whether that's going to be the last stop of the roadmap or whether we're going to go to the next step with a higher voltage.
Right, right. Oh, well, I think there are no further questions I see in the chat box. So let me again end by thanking the audience and, of course, thanking you most of all. So for Davide for taking our time and giving that wonderful presentation, patiently answering all our questions. So again, thanks and shout out to Dr. Ritu and Dr. Pooja from Samix and the PELS IES chapter of IEEE Bombay section for making this talk happen. And of course, again, many thanks to our speaker of the day, Dr. Davide, for his lecture. And we hope to have you in India and hopefully in Bombay sometime soon. Thank
The
you. Thank you,
gateway
David.
through the gate of India, yes.
Yeah.
Thank you so much,
Thanks.
Davide,
Silad. Thanks so much.
Davide, thank you so much again. It's a wonderful talk. I have a few questions, but I'll chat with you offline. But thank you very much. Wonderful talk. And of course, we'll connect more on the PSMA side of things as well. So
Absolutely. Thank you so
yeah.
much, Dr. Ritu. Thank you so much. Really appreciate it.
All
Thank you,
right. Thank
everyone.
you, Siladri.
Have
Thank
a
you.
good
Thank
night. Have a good evening.
Yeah. Thank you.
Bye,
Everyone.
everyone. Thank you. Thank you.
Bye.
Thank you. Bye.
Thank you, David. Thank you.